This is chapter 7.3, long functions as inverses. Woohoo!
In order to solve the exponential equation 2x equals 16, we need to think about rewriting 16 as a power of 2. 2 is the base raised to the x power. Well, 16 we know is 2 to the 4th. So once we can get the same bases, if we have same bases, we know the exponent should be equal because 2 to the x should be equal to 2 to the 4. So therefore x equals 4. So we need those to be equal. Therefore x equals 4. What about the equation 2 to the x equals 10? Okay. Now 10 can be broken up into 2 and 5, but we cannot make 2 to some power equal to 10. So to solve this equation, we need logarithms. And then note, a logarithm equals exponents. Every exponential equation can be written in log form. For instance, 2 to the 4 equals 16. 2 times 2 times 2 times 2. What we can do is we can write it as 4 equals log base 2. So the 2 is a little subscript. 16. Okay, so what we're going to practice on is we're going to look at taking our exponential form and writing it as log form, and then we need to go back from log form to exponential form. So equivalent exponential and log forms for any base b, okay, b cannot be equal to 1. We know that b to the x equals y. Therefore we can say, and usually it helps to always write the log first and the base, log base b y, and then equals x. So our x equals log base b y. So what we'll notice is this is going to be your exponent. This is our base. This is our answer. That'll help. Base exponent equals number is equivalent to the exponent, which is equal to the log of base to the number. So practice when the base of a log is 10. Okay, this is called a common log. A notation log base 10, 5 is really equal to log of 5. Okay? In other words, if you notice on the right hand side one, normally we don't usually put the 10. It's a common log. It's the common log that you find on your calculator when you have the log ln. It's to the base 10. Okay? So using our calculator to compute to the nearest hundredth, what we're going to do is we're going to say log base 10, 12 is equivalent to, and then round to the hundredth in terms of the answer. We need to write each equation in logarithm form. We need to start with the exponent. Okay, so if you start with the exponent, this is one way we're going to do this. We have 1,000 is equal to base 10 to the 3. So if we start with the exponent, we're going to go 3, which is equal to log. Okay, then we're going to write the base. Well, the base is 10, and then the answer is 1,000. So 1,000, which is equal to 10 times 10 times 10, we're going to write it as a log form as 3 equals log base 10,000. Okay, B. Start with the exponent. We know the exponent's 1/4, which is equal to log base 81, and the answer is 3. And C. Start with the exponent. Exponent is -2, which is equal to log base 5, 1/25. Another way to do this is if we have log form and we need to go to the exponential form, we're going to write each equation in exponential form. Start with the base. How low can you go? Start with the base. So log 32 equals 5. Which one is the base? Well, the little subscript next to the log, there's our base. So 2, remember, it is always equal to the exponent. So 2 to the 5th equals 32. One way of thinking this too is, I know if I end up writing it, so 32 to the 5th, that does not equal. If I end up writing 2 to the 32nd, that does not equal. If I wrote 5 squared, that does not equal 32. And if I were to do 532, I know those don't equal 2. So sometimes you can check back. Okay, B, we know the base is 144. The exponent should be the equal part, so 1/2 equals 12. The square root of 144 is 12. And the last one, we know the base is 3 to the -3. The reciprocal of 3 is 1/3, and then cube it, so 1/27. When a base of a log is 10 now, so the last couple examples. We had base 2, base 144, base 3. Okay. What if it's base 10? Okay, we call this a common log, and this we normally find on our calculator. The log function is a common log of 10. So we can say instead of log base 10 5, this is really just log of 5. With the it's not really there, but there is a base 10 that we usually don't write. So if we're going to use our calculator just to compute to the nearest hundredth, we're going to take our handy dandy calculator. We're going to plug in log. So over here on the left, we're going to hit log 12 parentheses. Notice it doesn't show a base 10, but it is using base 10. We hit equal to, we get 1 point, and we have to round to the nearest hundredth, so 1.08. If we do the next one, we have log of 0.5, log base 10, so log 0.5, parentheses, hit equal to, we get negative 0.30. A and B on the right, we need to solve x to the nearest hundredth. Convert to log form. Okay, so we need to convert these to log form and then hopefully solve. Okay, we do have base 10. It's in exponential. Go ahead and write the exponent first. So x equals log base 10, 31. And then if we go the other one, we're going to go exponent is x equals log base 10, 3/49. Both of these are base 10, so we can plug in the answers using our calculator again. So we'll go log 31, hit enter. We get 1.49, round to the 100. So it's approximately 1.49. If we do log 3/49, some of you 3 divided by 49, we get negative 1.21. Make sure you may not have the same calculator as I do. That's okay. Do make sure you know where your log button is, where your Euler's number E function is, and your ln button. Graphing. What does it look like when we graph? Okay, so if we have the same function, if you remember, we had 2 to the x. So if we plug in negative 2, we should have had 1/4. Negative 1 is 1/2, 1, 2, and then 4. If we graph this, if you remember, we get the function here. This is our y function. So what we need to do is the graph of the inverse of 2 to the x. Remember, if you remember with points, we take the x and the y and we switch them, y versus x. Okay, now we can find the equation in a second. So if we remember the inverse part, negative 1, so now it becomes 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, 4, 2. We're going to get a function. And if the other way, you remember, if we have this y equals line, we can fold on that dotted line, and you're going to get this function here. It's going to hug now the y-axis down and then go up. This one, which is underneath, this is going to be our y to the negative 1, or we can call it the log base 2 of x. Now, question, how did I get that? If we switch over to the right-hand side, to find the equation of the inverse, if you remember what we did, we take and we switch x and y. So we go x equals 2 to the y, and then we rewrite it as a log. So y equals log base 2 x. So inverse of exponentials are logs, inverse of logs are exponential. Okay, if we look at the two graphs, domain. Well, if you remember our domain was for the original exponential 2 to the x. X is the set of all real numbers. Okay, and our range was y was greater than 0. Now if we look at y log base 2x, which is the inverse, we now get a domain of, so we look at the x values. Well, looks like the x value doesn't go past 0, and then everything to the right. So we're going to say that x has to be greater than 0. So there's that asymptote that looks like right on the y-axis. And then our domain, which is y, kind of switching the domain and range, we know that we can go all the way down to a very low negative on the y, all the way up eventually on the y to the positives. So we know that y is the set of all real numbers. Moving on to the last one, if we need to graph y equals log base 3x, let's rewrite this as exponential form. So base first, exponent y equals x. Okay, so let's look at we need to find the x's based on the y that we put in. So let's use values to input in the y first to give us our x. So if we plug in 0 for y, okay, 3 to the 0 is 1. So 1, 0 ends up being a point. If we plug in 1 for y, okay, 3 to the first is 3. Just backtrack a little bit. Let's try -1. So if I plug in -1, you end up getting the reciprocal of 3, which is 1/3. If we try 2, or -2, we get 1/9. Now let's go back the other way because it looks like it's going to get smaller and smaller. Let's go to 2. Well, 3 squared is 9. And that's a little bit further off our graph than we're used to. So if I go and I plot these points, we get this graph. If we notice, it's not going to approach this 0, and it's the log function. So if you remember, the domain is greater than 0, so we have this imaginary line that's dotted. That's our asymptote. So give the domain. Domain we know from 0 on. So we're going to say that it's all the set of x's such that x is greater than 0. Okay. Our range, notice the range goes all the way negative, goes all the way up to positive. So if you remember from the last page, we know the set of y's such that y's are all real numbers. Okay. Our x-intercept, where it crosses the x-axis, is 1, 0. And our asymptote, which is this vertical line, remember, if you remember, vertical lines are always x equals. So this is x equals 0 is our asymptote. If we use a different color, I'm going to use a different color, we need to graph y equals log base 3 x minus 2 plus 3 on the same axes. So in other words, we need to figure out what the transformation is from the parent graph and then give the new domain and range. We're going to use the same as the exponential form in terms of the same properties that we use to do shifts. So for instance, if we look at our equation and we change the x part, okay, we actually are minusing 2. Well, what makes that 0 is 2, and 2 is to the right. So what you're going to see is this line right here, this asymptote, it's going to shift twice. Or all of these points are going to shift twice. Okay, and then we're going to plus 3, which means a vertical shift. So our line is going to move over 2 and shift up 3. So what we should get is in green, we get this new graph. And then also we get this new asymptote that just shifted to the right 2. So now we have a vertical x equals 2 for a new asymptote. Okay. Domain and range now changes to, or let's do the list of the transformations. So what's happened from the parent? We've gone right 2 and up 3. Okay. Our new domain and range is the set of all x's such that x now has to be, if you look at the green, it has to be now greater than 2. And our range is the set of all y's such that y is still every negative up through positive. So it's the set of all real numbers.
Do you best forget the rest? Bye now. Bum, bum, bum.